Hey, how's everyone doing? Good to see all the folks here. Please drop in the chat. Where are you joining in from? Hey, how's everyone doing? Good to see all the folks here. Wow, I see a ton of responses. People are joining in from all over. Texas, Massachusetts, Toronto, Nairobi, oh wow, London. Saad, we have people from all around the world to come see you. How do you feel? You're we can't hear you actually. Morocco, wow, Texas, Ghana, wow. And drop in the chat, what are you looking forward to learning in this workshop? Want to make your own LLM, out of the box idea. Making your own LLM. Nice. Who here has like a NVIDIA GPU or Mac Mini or just a device powerful enough to run an LLM on their own device?
Hello. Guys, can you hear me now?
Okay, yeah, we can hear you, Saad.
Okay, perfect. Faizan, I'll start officially at 5:10.
Yeah.
But let me give a brief introduction in the meanwhile. Um,
Wait, do you mind if
so
I'll share a bit more context and then you can go.
yes, yes, please. Yes,
Uh,
yes, yes.
So, see a lot of answers coming in the chat. This is great to see. But yeah, thank you everyone for joining this workshop. It's going to be super exciting. Just for a bit of kind of background, so my name is Faizan. I'm the co-founder of HeadStarter. This event is hosted by HeadStarter. And at HeadStarter, we're building a community of software engineers and a platform where engineers can compete with each other on challenges and different projects. So I'll share more about that at the end of the workshop. But I just wanted to give a bit of a background on how I met Saad, because I think it's an interesting story. Saad is the one who's hosting the workshop today. And the way I met Saad is through Powell House. So Powell House is a house in San Francisco, California, that has produced six companies that have been funded by either YC or A16Z, which are top investors in Silicon Valley. So for each of those companies, the founders of them met each other through living in Powell House. And so, we've created an incredible community here of founders, engineers, and I met Saad around 3 months ago when I first moved into Powell House. And I knew that he was very sharp just by the way he articulates himself. And I learned later on that he was studying to be a lawyer. So, all of it started to make sense. But, so let Saad introduce himself in just a bit. But I just wanted to share, the beauty of being in SF is that, over the past couple months, I've seen Saad go from just like an engineer, working at a company. It was a very good company, by the way. Shad can share more about that. But I've seen him go from an engineer at a company to now being a founder of a YC-backed startup, raised a seed round, and is actively also like hiring folks as well. So, in just 3 months, he's generated a lot of revenue, he's got investors, and raised a seed round of funding. So it's incredible how much he's achieved in just a short amount of time. And I'm super excited to see him do this workshop today. So Saad, please take it away.
Awesome. Faizan, first of all, you are far too kind. Any compliments, please. I reject those. But Faizan is a great close friend. Let me kind of get started with telling you guys a bit of my story and then about what I envision the next month to look like. So first of all, as Faizan said, yes, I am a member of the Powell community. If you guys go to powell.st, you can learn about Powell House. Faizan and Yassine from Head Starter put on events every 2 weeks. But I'll tell you a bit about my life story, how I got into Powell, and how that basically completely changed the trajectory of my life. So I always wanted to go to law school. Ever since I was a child, I was enamored by public speaking. I love Supreme Court cases. I think the law is like a really beautiful, amazing field. I was born and raised in the Bay Area, and my dad had always told me that if you go to law school, you have to pay for it yourself. So my singular goal throughout college actually was to figure out what major or what career path would make me the most amount of money so I could fulfill my dream of going to law school. And that ended up being tech. So I majored in computer science. I graduated from Berkeley in 2021, and I ended up working at Tesla on the full self-driving team for about 2.5 years, working on ML infra. And I absolutely fell in love with ML infra engineering. I thought self-driving cars were the coolest thing in the world, and I felt very fortunate that for a brief period of time, my manager's manager was Andre Karpathy. So I was just surrounded by these like really amazing computer vision researchers, the best of the world. I was doing some infrastructure work, nothing too crazy, but the software engineering that basically allowed us to train these large neural networks where 50 to 100 million video clips are being trained that helps a car drive itself. So that's kind of my story. I did end up going to law school for a year, ended up not liking it that much, ended up coming back to San Francisco where I lived in Powell House, which is our Hacker House community. And from there, I basically ended up starting my own startup, which is called Claybird. We are an AI ads and video marketing agency. Would love to answer any questions about that afterwards and the YC journey if you guys are curious. But because we're a little bit short on time, I'm going to go ahead and share my screen, if that's okay, Faizan, and we will get started. Let me give a brief introduction actually before I share about what we're doing in this lecture and over the course of the next 3 weeks. So I know it was advertised that we're going to build our own GPT. That is true. We are going to do it, but we're going to take things slow. And we are going to train our own LLM. We're going to make a version of GPT-2 over the course of the next 4 weeks, but we're going to do zero to hero. So obviously, as someone who worked for Andre Karpathy before, I love his stuff. And everything that I'll be sharing today is a simplification of a YouTube series that he has online called the Zero to Hero series. So I'm not really coming up with anything new, nor should I. He is an amazing researcher and has done a lot for machine learning education. So we're going to be roughly following his syllabus. So in today's lecture, we're going to cover the brief. I see there's a lot of questions in the chat about it being recorded. Yes, this is recorded, and the Faizan will take care of distributing the recording afterwards. Going back to the series, today we're going to focus on what is a neural network, how do I build a neural network from scratch, how do I implement backpropagation, and how do I train a neural network, right? So we're starting from the ground basics. If we're not able to build a neural network, then none of the stuff that we're going to talk about next week, which is a basic language model, not even an LLM or a GPT, but a basic language model. And then in the third and fourth week, where we're going to actually build out GPT-2, if we can't do this basic level of figuring out how backpropagation and training neural nets works, then none of that other fancy stuff is going to make sense. So for those of you in the chat that are already so used to training LLMs and have a lot of machine learning experience, this is going to be a lot of review. But I still think it's very useful. And I also think for a lot of you folks that are interviewing for ML infra positions, one of the questions that I used to ask at Essential AI, which is Ashish Vaswani's research lab, to potential candidates was implement backpropagation from scratch. So we're going to literally go through that interview question today. And if you can do that, I think you have a very good understanding of ML. So Shlok is asking, for example, is this not for pure beginners, or is this going to be a very mathematically heavy discussion? Nope, we're going to start at the basics. What is a derivative? So we're going to get into that in just a second, but let me share my screen. Fizan, can you just confirm, can these guys hear me okay?
Yeah, they should be able to.
Okay, even now, right? I'm just taking out one earpiece.
Yes.
That's fine. Okay, and can everyone see my screen?
Yes.
Fizan? Okay,
Yes.
perfect. Fizan, feel free to interrupt me if I'm going too far, but This is a Jupyter notebook. Everyone's going to share my screen. We're going to walk through a very basic exercise together, which is going to be what the hell is a neural network? What is backpropagation? How do we train these models? And once we know what a multi-layer perceptron is, we're going to go from there. But first of all, let's go a little bit of history. So multi-layer perceptrons were basically founded in the 1970s. And there was, a very famous paper that basically talked about how you could use MLPs on what's known as the MNIST database. The MNIST database is a group of a bunch of images of numbers that are basically labeled. Right. So these, for example, are people have gone on in the 1970s and they have written out with their hands numbers. And each of these images is labeled with what number it is. And this was basically the impetus for early machine learning back in the 70s was, are there ways that we can basically take a very general form of labeled data, which is having us write down numbers on a piece of paper, and train a model that, it's kind of difficult. You can see like with all these numbers, there's so many different variations of the way that people write the number 2 or write the number 4. And we want to know, is there some way that we can basically build a model that is so general that can learn from all of the data and be extremely rich in its ability that any new sample that comes, it can accurately predict what kind of number that is, right? So that's where we're going to talk about the multi-layer perceptron. We're going to talk about neurons. But I guess before we get into building out these models, that's kind of our initial motivation right here. I want to talk about the most basic element of any good neural net engine, and that's what's called autograd, or in this case, micrograd. So if I search up on GitHub micrograd, you'll see Andre Karpathy has a really nice tiny scalar vector engine, which is a small autograd engine. So neural nets are quite straightforward. They're basically layers, linear layers, where we have multiple different neurons. Those fire multiple layers that are stacked on top of each other with a small nonlinearity in between. And these neural nets are extremely expressive functions. So neural nets are basically capable of like fitting any kind of model, right? There's something called the universal approximation theorem, which says that any function, sine of x, cosine of x, whatever, these neural nets are capable of approximating them given enough layers and given enough depth. Now, we're going to talk about what that means in a second, so forgive me if I'm kind of moving a bit fast. But today's purpose is simple. We want to build an autograd engine. So what does that mean? Whenever you work in PyTorch or Keras or any machine learning library of your choice, you're going to be working with tensors. Tensors are, of course, vectors that have multiple dimensions. You want to make sure that whatever operations you do to these vectors, you are able to store the gradients. So for example, if I look at this code right here, I have A and B, which are two values. I can add them. I can I can do A times B plus B cubed. I can do C plus 1. I can do all these kind of mathematical formulas to it, right? And then once I end up at the very end, G, I'm basically going to do G dot backwards, right? So what that does is it's saying that final tensor that is the result of A, B, C, and D that are all these different initial values. It's going to allow us to calculate the derivative of G with respect to A. So I'm going to say that one more time. I have A, B, C, D, E, F, and G, right? These are all different values that I started off with, namely -4 and 2. I performed a bunch of intermediate arithmetic on here. You see, I take A and B and I add them. I put that in C. I take A and I multiply it by B and I add it to B cubed. I put that in D. I add 1 to A plus B, right? I'm doing all this kind of math. And at the end, I have a final value, which is G. I want to know at the end of it, what's the derivative of G with respect to A? And what's the derivative of G with respect to B? That's A dot grad and B dot grad here. Now, you guys might be thinking, guys, Saad, I took basic calculus. I know how to do, the multiplication, the power rule, right? I could write out a super long expression for this mathematical formula, and I could solve it. And you'd be right. For that one equation, you'd be totally right. The problem is that neural networks, modern day neural networks, have hundreds of layers. They have tens of thousands. Actually, GPT-5, for example, has almost 1 trillion parameters, right? So if you wanted to go ahead and write out every single mathematical equation and try to determine the initial inputs, how does wiggling those initial inputs influence the final output? It's just too much. So this is the first reason, it's our motivation that when we build neural nets, we want to be able to add, multiply, subtract, perform operations on numbers, and take those outputs and understand very precisely that how are those outputs shaped by our inputs. All right, I'm going to pause for a brief question there. That's just the kind of motivation. Is everything kind of clear so far? What's the significance of a gradient? So one more time, in neural networks, we have multiple mathematical operations that happen, right? We have initial inputs that come in. Our inputs can be anything, right? Our inputs can be an image, and images are coded as pixels. They can be words. Each word, for example, on ChatGPT is a vector. Word to vec is something we're going to implement later. And then we're going to multiply and add those vectors together. And at the end of it, we're going to have an output vector. We're going to call backwards on that. And we're basically going to try to understand how does that output vector, how is that influenced by the inputs? So in this case right here, when we call the G dot backwards, it allows us to build up a directed acyclic graph, a graph of, and I'm going to show you this visually in just a second, a graph of everything that happened here. A and B were added, A and B were multiplied. The outputs of adding and multiplied were multiplied by each other. And then we can understand what is the derivative of that output with respect to A. So in this case, if it's 138, that's saying that small manipulations to A will have a 138 times effect on the output. And you'll see over here, for example, in this mathematical expression, if we manipulate B a little bit, it's going to be 3 times stronger than wiggling A. Right. And this is the purpose, the bread and butter of machine learning, which is how can we have understand that for all the little dials and whistles that we have in our neural nets, the billions of parameters, right? Like GPT-5 has 1 trillion parameters. How does wiggling even a single weight affect the output? The output is going to be a loss function, but we're going to kind of go on from there. All right. That's kind of some high level philosophical stuff. Let's start coding. I think everything will be clear once we get into that. All right.
Saad, one thing, are the folks here able to like follow along with you? Like, can you
Yes,
like put this
100%.
on
So the
GitHub?
code is, yeah. I would recommend that you guys just follow along as I type. I'm going to type really slowly, and we're going to build everything from scratch. So literally begin with the blank Python file. All right, is that cool? I've just put it into a Jupyter notebook so I can lecture better. Is that okay, Fizan?
Oh, I see. So you're saying like they can just start with a blank Jupyter notebook?
Yes, 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 yes. Yeah.
Okay.
All
And
right.
actually,
Yeah.
to make it easier for them, it can be like a Google Colab one, so they don't have to configure any like, you know, local settings or anything. So
Yeah.
I'll just share like
You
Google
we're
Colab.
gonna start. Yeah, you have a Google Colab already that you've shared?
Yeah, I'll just
Okay,
share in the chat.
perfect. Um, I can upload the file that I have is so basic. There's really nothing in there. Like we're really starting from scratch. Is that okay, Faizan? I don't think we even need to
Yeah,
have.
sure.
Um,
And one thing, can you talk a bit slower? I know you have so much going on in your mind, so many things you want to
yes,
say.
yes, yes, yes.
So
Okay.
yeah, if you can talk a
I will
bit
slow down a
slower,
bit. Yeah.
that would be
Yeah, no
better.
worries. No worries at all. 1 second, guys. Okay, so I'm gonna send this link back in the chat, Faizan, if you just want to give that to everyone. Let me
Sure.
know if that's fine. Again, we're gonna really be starting with complete basics. So you don't even need, I would not recommend using the Jupyter Notebook. I would recommend just firing up a Python file. The libraries are going to be super simple. We're literally just importing the math library, NumPy, and matplotlib. Yeah. All right. I'm going to get into it, guys. If there's any issues with you guys following along, Faizan will interrupt me. All right. Cool.
Oh, one
So
thing.
yeah.
Sorry. One thing before we begin, guys, please take, like a screenshot or a picture of Saad right here. Make sure to post on LinkedIn that you're being active and learning about ML. Because, one thing, Saad, you didn't mention is how you were at an event with Ashish and you were
Yes.
offered offer on the spot. But yeah, please take a screenshot of Saad, post on LinkedIn, share, that you're actively learning ML, and I can almost guarantee you'll have opportunities kind of come your way from
Yeah.
just showing that.
Yeah, I'll share that story during the intermission about how important networking is and how I actually ended up getting a job at basically because of one of the events that I had attended. All right, I'm going to kind of go into this. So, like I said, we're building an autograd library. So the purpose is to take mathematical values, add them together, multiply them, and get their derivatives. It's as basic as that. And we're going to see in a second how that builds up a neural net. But again, all I want you guys to know right now is if I take A and if I take b, I add them and I multiply them by 2, right? I want to know what's the derivative of this function with respect to a, what's the derivative of this function with respect to b, right? So first of all, starting with complete basics, all right, guys, what is a derivative? The most basic definition of a derivative comes from this limit definition right here, which is that derivatives are, if I have a mathematical expression, how do small changes in the input, in this case, if I have a function f of x, and I change it by h very, very slightly, how does that influence the output? Another way of calling a derivative is what's the slope of a function at a given point, right? So what we're going to do is we're going to take a very basic function. This function is f of x, and let's do 3x squared minus 4x plus 5, right? So if I do, for example, f of 3, let's do this in our heads. 3 squared is 9 times 3 is 27, minus 12 is whatever, plus 5, who cares, is 20, right? There you go, right? Very basic function. If I'm going to graph this function, you're going to see right here, this is a parabola. It's a parabola whose vertex is at 2/3. Again, a vertex is a place where the derivative is 0, right? The slope is 0. And the purpose of calculating a derivative is we want to know what the slope is at any given point, right? So let's say, for example, I have this h, which is 0.0001. My point being is, let's say, for example, I'm going to take f of 2/3, which, as we know, is 3.6667 right there, right? And I want to know what is the slope at that point. Now, one way of doing that is basically saying, okay, if I were to take that point right there, that's the vertex. And if I were to slightly nudge forward by a small value h, and if I was to divide by that difference, then what would my slope be? So in this case, for example, if I take that like a super, super small h, right? And if I do, let's say x is 2/3, right? That's the vertex. And if I do x plus h, a very small change, minus f of x. So everyone see this so far? We're going to f of x, and we're very slightly increasing by the value of h. And then we're going to divide by h. Again, if you guys have taken Calc 1, this is literally the limit definition of calculus, right? This is the limit definition of a derivative. So once I take that value, what do I get? I get 0, right? So this is some jumble of math, e to the negative 0.7. You guys are going to see this a lot. Whenever we do floating point arithmetic, you never get precise values. That's just the nature of computers because they run in base 2. But just trust me when I say that this number is 0, right? Like if
Stop.
I, yeah,
Can you talk a bit slowly? The folks here, they're like struggling to keep up. They
okay,
said.
yeah. I'll talk a little bit slower. All right, so we're good so far. Basic derivative, right? Let's get a little bit more complex. Let's say I have a function, which is I have a is equal to 2.0, I have b is equal to negative 3.0, I have c is equal to 10.0, and then d, this is my final function. It's going to be a times b plus c. A very similar, a very basic multivariate function, a, b, and c. Now let's go ahead and print d. So as we know, 2 times negative 3 is negative 6, plus 10 is going to be 4, right? Now I want to know what is d with respect to a, or what is d with respect to b? What is d with respect to c? As in, if I derive this function, how do small changes in the input influence the output, right? So again, we're going to repeat our same limit definition of a derivative. We're going to take a very small nudge, that's what we're going to call h. We're going to take each of our inputs, which is 2, negative 3, and 10. And then we're going to basically take d1, which is going to be a times b plus c. We're going to slightly modify c. So in this case, we want to know what is dd with respect to c. How do small changes in c change the output d? So again, we're going to see that right there. We're very slightly changing c by 0.00001. And then we're going to say D2 is the same thing, A times B plus C, right? So now if I have D2 and I have D1, you'll see they're very, 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 similar right there. Now let's go ahead and, I can print, let me just print that a little bit neatly. So that's D1. And then I've got over here, excuse me, D2. And then what is the slope? Remember, slope is rise over run, or again, in the limit definition, it's D2 minus D1 divided by h, right? So that's the slope right there. And boom, right there. Our slope is, I think I did, my parentheses are all over the place, is 1, right? So let's just make sure that makes sense to us from a multivariate perspective. If I have a times b plus c, this function is called d. And I want to know what's the derivative of this function with respect to c. Remember, in multivariable calculus, if I'm doing dd over dc, these two values, they don't matter. They go to zero, right? And what's the derivative with respect to c of just c? That's 1, right? Because 1 times c, as we know from calculus, 1 times c, the derivative of that is just simply 1, right? So we have successfully done a very basic derivative, right? All right, we're going to continue on. So now we know what a derivative is. Derivatives help us get a slope. Derivatives help us understand how do changes in the input affect the final output. Let's go to a very basic value object, right? So a value is what we're going to use to store our inputs. And I'm going to even delete this and totally start from the beginning. So I'm going to make a class in Python called value. Let's go to the init function. The init function is going to say value is going to take in some data. You know, store that data right there. We're going to use a repr class. As we know in Python, a repr class allows us to print out the value and kind of see what it looks like. So self.data right there. Put a close parentheses there. And let's also do, let's just keep it that simple. So let's say I have a value of 2, right? There we go. I forgot my close parentheses. Sorry, guys. There we go, right? So a value of 2. I got a value of 2. I got a value of 3. All this class is doing is just a wrapper around a number, right? Now, let's add 2 numbers, right? So adding 2 numbers is really straightforward. I'm going to take self. I'm going to take other, which is going to be another value. I'm going to say that result is going to be value of self.data and other.data, right? Boom, return that thing. Easy peasy, lemon squeezy. If I have value of 3 plus value of 4, 3 plus 4 is value of 5. What happened here? Unsupported types for value of value. Let's see, what did I do right here? Return other. Let me do this. A is equal to value of 3. B is equal to value of 4. Oh, I need to run this cell. My bad, guys. Forgot to run the cell. There we go. Value of 7, right? Pretty straightforward. We have a value class that can add 2 numbers. Let's implement more functionality. We shouldn't just be able to add numbers. In linear algebra, you want to add and you want to multiply, right? So let's do the same thing right there. So out is going to be a value of self.data times other.data, right? Boom, return out. Now we can do 3 plus 4 is 7. 3 times 4 is 12. Okay, boom. Same thing. I need to run my cell before I hit enter so prematurely. So there you go. Now we can multiply numbers. Cool. What else can we do? I don't know. Let's say I have, A, which is 2, and I have B, which is -3, and I have C, which is a value of 10, right? I can basically chain this stuff. So I can do A times B plus C. Is that going to work? Let's see. Yeah, it does, right? So it's doing, it's a value class. I can add and multiply numbers, right? Yes, we're going to get into power and everything else in just a second. But again, the whole point of an autograd library is not just to be a wrapper around numbers. It's so that when we do these operations, we have pointers to each one of our children. So we want value to store every mathematical operation's inputs and outputs. So for example, if I do A plus B is equal to C, I want to make sure that C's value object knows that it was the result of adding A and B. Well, that's super basic. All I have to do is I'm going to make self.prev, which is short for previous. It's going to basically just have the children. And what this looks like is that when I add 2 numbers, I'm going to say, hey, listen, when I added, let's say, 2 and -3, the result of that should store as a tuple self and other. Same thing over here. We should store self and other. I think it's also really nice if we can have some labels here too. So I'm going to have this op variable that's basically going to tell us, hey, what was this value, the result of like what kind of operation? So for example, if I add 2 numbers, I want to store right here that this was the result of plus. And if I multiply 2 numbers, this was the result of a multiplication, right? Again, I know I'm going a little bit fast right now, but this stuff is a little bit basic. Let's see, where did I mess up? Cannot assign to expression here. Maybe you meant equals equals. 1 second, guys. Let's just do right here, A plus B. Value of 2. Oh, I forgot to give it to children. So children is going to be an empty tuple as a default, right? So now we can see that if I have C is A plus B, C is storing what are its children, A and B, and it also knows what are its C operation. It's C is the result of an addition operation. Cool. So is everyone with me so far that we're able to have a very basic value class that can add and multiply numbers? And as we go ahead and chain this kind of stuff, like if I go back to the, A times B plus C, I know that D is a result of a multiplication between two values, -6 and 10. Everyone with me so far? Cool. Now let's visualize the DAG. I'm going to copy paste some code here. You guys can, I'm going to even chuck it into the Zoom chat just so you guys have it. It's really not that crazy. We have a very simple BFS right here, and we have a very simple visualizer right here. I really wouldn't worry about this. You guys don't need to have this in your implementation. It's just easier for me to teach. But let me go ahead and take my what's it called, value object right here. And let's see, I've got an operation. Let me also just have a label. It's really nice to be able to like label this kind of stuff so I know what the name of each class is. But other than that, I'm going to have this, let's set the label. This one is going to be called A. This one is going to be called B. This one is going to be called C, right? And then of course, D dot label is going to be D, right? So now when we use this function right here to draw our compute graph, if I do this on D, has no value grad. 1 second, guys. Let me just delete this. Sorry about that. Boom. So very straightforward. We can see that A and B got multiplied. -3 times 2 is -6. And then -6 got added to 10. And I end up with D, which is 4. So hopefully, again, things are pretty straightforward. We're building very basic compute graphs of multiplication and addition. Cool. Let's keep going. And in this time, we are going to have a slightly longer what's it called, function. So in this case, we're going to have A, B, and C, same thing, 2, -3, and 10. We're going to do A times B plus C. This time, let's also have a function E, which is A times B. Let's also call D, E plus C. And let's kind of just basically have a more complicated compute graph right here. So if I do draw dot of L, my kind of final function right here, you can see I have a multiplication, I got an addition, I got a multiplication, and everything like that. Again, if anyone showed up late, I think I saw Lucy showed up a little bit late. We're just making very basic compute graphs off of our value function, which allows us to add and multiply numbers. All right. So cool. Now you're thinking, okay, Saad, this is like really stupid. Like, why did you make us do this? And my answer is that we now want to be able to say, okay, what is the derivative of D with respect to C? Or what's the derivative of D with respect to A and B? And in the future, we're going to have these really long compute graphs that have like thousands of nodes that represent a neural network. And we want to know, how is that final node at the very end? How is it influenced by the million different weights that we can tweak when we're doing our neural net training, right? So let me just do one thing right here. So there you go. You got A, B, C, E, D, F, and L, right? Okay, so now my question is, most basically, let's begin with a gradient. So let's tweak our, what's it called? Our function right over here, draw dot, to also visualize as well as the actual node, but what the gradient is as well. So I'm just going to put, just 1 second, guys. Right here, the grad, we're going to store that as %0f. So it just gives us, the format of it. And let's have the gradient as well. So in our value object, I want us to also have gradients, okay? So that should be pretty straightforward. We'll say self.grad is initialized at 0.0. And kind of going forward, we're going to try and figure out what the gradients are. Okay, cool. So let's visualize this one more time down here. Okay, cool. So again, all the gradients are empty, right? So the most basic thing is what is the derivative of L with respect to L? If anyone can type that in the chat very quickly, this should be quite obvious. What's DL over DL? 1, right? That's exactly right, right? So yeah, so many ones in the chat. Very good. That's quite straightforward. So we can basically set that right over here. So we can say L dot grad is equal to 1.0, and then we can do, draw dot of L, it's going to populate that there. I just want to very quickly do the limit definition as well. So for example, if I have A, B, C, D, E, F, and L, just like I had before, and in this case, I'm going to have L1. Same thing, I'm going to have the same values, but now we're going to very slightly tweak L. So this time, L is, let's say, plus H, right? You're going to see right there, if I call this function, let's call this function LOL. Boom, okay. The derivative of L with respect to L is 1, right? Nothing straightforward, nothing too crazy there. The next thing we want to kind of figure out is, okay, well, we know derivative of L with respect to L. That's not that exciting. How can we figure out derivative of L with respect to D or derivative of L with respect to F, right? So we're going to kind of go onwards and we are going to try and calculate that, right? So let's do this right here. Verify DL over DD, right? So really quickly, let's say if L is equal to D times F, right? That's what we have in our chain right here. Then what is DL over DD? Well, that should be pretty straightforward, right? Let me put this in raw. So if L is D times F, the limit rule of calculus is going to say, again, same thing. I take f of x, I slightly tweak it by a value h. I subtract those two and I divide by h. So if I apply this here, I'm going to have d plus h. Actually, in this case, yeah, we're trying to do dd. So we're going to slightly add a value to d. D plus h multiplied by f, right? That's f of x plus h minus what's called df, and all of this divided by h. Well, let's simplify this. That's df plus hf minus df all over h, right? So these df's cancel out. We're left with hf over h. Boom, we're left with f, right? So again, very basic multivariate calculus that if I have L is equal to D times F, the derivative of L with respect to D is whatever is being multiplied. So that's F, okay? So now we know from a limit definition that that's certainly the case. So let's go ahead and write that in our chart. So L dot grad is 1.0. D dot grad, let's see over here. So the gradient of D is going to be the thing that's multiplied to it, which is -2. And the gradient of F is going to be the thing that's multiplied to it, which is 4, right? So D dot grad is equal to -2, and F dot grad is equal to 4, right? So now if I go ahead and draw this, same thing, we're going to see gradient is filled out over there. Why did I not fill that out? Just 1 second, guys. Let me verify I labeled everything correctly. Yeah, so there we go, right? We've got our gradient. We've got the gradients are exactly, what they should be, right? Okay, now we are going to go to the crux of backpropagation. Backpropagation is the idea that, okay, sure, Saad, you're probably thinking, okay, well, doing a derivative of like one operation is really straightforward. Everyone knows that how to do the derivative of d times f. But the difficult thing is how do I figure out how do small inputs that have like thousands of operations between the input and the output, how do they relate each other? So now we're going to go to the crux of backpropagation, which is figuring out DL with respect to DD was pretty easy. But now we want to know, okay, how do small changes in C or how do small changes in E affect the output L? Again, L is going to be our loss function. We're going to talk about that in a second. So let's go to chain rule on Wikipedia. Chain rule tells us, I like this definition a lot, that if I have 3 variables, X, Y, and Z, and I have some kind of arrangement where they're chained of each other, then the derivative of Z with respect to X is going to be multiplying each step along the way that takes us there. So in our case, if I want to figure out the derivative of L with respect to E, I need to do derivative of L with respect to D and derivative of D with respect to E, right? So that's the same thing with C over here. So I'm just going to write that so everyone totally understands that very clearly. The derivative of L with respect to C is going to be the first hop, which is derivative of L with respect to D, and then multiplied by the derivative of L with respect to E. Now, I'm not going to go into the proof for this. You're going to trust me. But there's a very famous quote by George Simmons, which is, if a car travels twice as fast as a bicycle, and a bicycle is 4 times as fast as a walking man, then the car travels 2 times 4 equals 8 times as fast as the man. So again, you can see when we nest these mathematical functions with each other, every time that we open up that function and derive it, we multiply along the way. All right. So let's keep going. And now let's try and figure out DD with respect, DL with respect to DC, right? So let's say, sorry, just one more time. Let's do DL with respect to DC. That's what we want, right? Let me put right here. This is what we want. Let me put that markdown. What do we have? Well, we know what DL with respect to DD is, right? That's the gradient right here. That's -2. We also know what DD with respect to DC is, right? If I'm adding two numbers, in this case, if D is equal to E plus C, the derivative of D with respect to C is again 1, right? So that's pretty straightforward, right? So we have these two values. All we have to do is say DL with respect to DC is, again, we are going to multiply these values. So DL over DC, in this case, we have that -2 value right there, multiplied by 1.0. DL with respect to DC should equal to -2. And if you repeated this, you would realize it's the exact same thing for DL with respect to DE, right? So when you add those two numbers, both numbers end up having the same gradient, right? So we're going to go ahead and update that. E dot grad is equal to -2. C dot grad is equal to -2. Boom, let's go ahead and draw our graph one more time. So you see, guys, we're slowly filling up what's the gradients for this entire function with respect to E and C. So Jay has a question as to what DL with respect to DE is. So Jay, one more time, DL with respect to DD is -2. Then we hop, we multiply it with what's DD with respect to DE. If D is E plus C, we just differentiate that. Right, so I'm going to write that just one more time. L is equal to E plus C, times, times F, right? So that is D right there. That's how we're kind of backing in. If anyone, Rohan is asking in the chat, what is the gradient? The gradient is a derivative. So a gradient is usually a vector. It's a vector of derivatives. We're going to get into that in just a second, but let's just use the word derivative, which is in the single variate case when we have one variable. Okay, cool. So I did that, using just the chain rule, and I told you guys to trust me about the chain rule. But why don't we actually let's verify DL over DC using the limit definition one more time. So I'm just going to put this in a function. I'm going to call it LOL, just so I have some separations of variable names. Let's say I have a very small change in H, and let me take my function one more time. So this is the exact same function we've been working with. We have ABC, multiply them, add them. This is the exact same thing we did in this graph up above. The only difference is now we're going to say, hey, let's very slightly tweak C dot data. See this right here? We're going to very slightly nudge C. And now I want to know, hey, what's L2 minus L1? L2 is the one where we very slightly nudged C. And we're going to divide it by H, right? So if I call this function, what do we expect? We're expecting -2 to come out here. And exactly what we get, right? There's a small error because of floating point arithmetic, but okay, we are right about the limit definition. I can repeat the same experiment instead of C, but now I can nudge E slightly. You'll see the same thing, right? So this is really powerful. Like we have these functions, we're able to very slightly nudge them, take the slope, and figure out if our gradients are right. We're going to do the very last step, which is what is DL, all the way with respect to our initial two inputs. And this is going to be really exciting for us because this is proving that we are able to figure out the gradients for each node. So Rohan, to answer your question, what is a gradient? It's how does each individual input, how does that affect our output, right? So I'm going to keep going over here, and we're going to say, okay, what is DL with respect to DA? Well, that should be pretty straightforward. DL with respect to DA, well, let's go down our graph. So DL, first we're going to do to DD, DL over DD, multiplied by, all right, what's the derivative of D with respect to E, right? So DD over DE, multiplied by, one more time, DE multiplied by dA, right? So this is our chain rule in action. Everything is, lining up pretty nicely here. So, well, let's calculate this out. dL with respect to dd, the gradient right there was -2. dd with respect to dE, we did that over here. It's also, let me just double check. It should be -2 again. Yes. And then dA, and this is the last piece we have to calculate. What is dE with respect to dA? And as you guys can see here, if E is the result of multiplying A and B, A times B, if I were to derive that with respect to A, that A falls out and the B is left over. So dE with respect to dA is going to be right here, that -3. So we're going to do -3 right there. So if I go ahead and calculate this, what's -2 times -2 times -3? I'm going to get -12. I just want to make sure I did everything right there. Just one second, guys. Actually, guys, forgive me, it's just a small mistake here. This number -2, that's the number right here. I actually don't have to do the whole chain again. I only have to start here. This number, -2, is how do small changes in E affect the total output? So you actually only have to look one layer up and then look at your current thing. So one more time. So dL with respect to dA is just going to be dL with respect to dE multiplied by dA over dA. So if that kind of makes sense here, when we do backpropagation, we only have to answer the question for the level that we're at right now. So for example, if we're looking at the node A, one level above, what is the derivative of the loss function with respect to that value, which is -2? And then how is that influenced by the operation that we're doing right now, right? Okay, so one more time. I think someone was asking in the chat, why are we multiplying these gradients? I think George Simon's quote is really useful here. If a car travels twice as fast as a bicycle, and a bicycle is 4 times as fast as a walking man, the car travels 2 times 4 equals 8, right? So when we nest these functions, and then when we derive them, getting their slopes, we're multiplying at each step. All right, hopefully that's clear. Cool. So let me just calculate this one more time. dL with respect to dE was -2 multiplied by dA with respect to dA is that -3 right there. So we're going to get 6. -2 times -3 is 6, right? Let's just verify that one last time using the limit definition. So if I have a function, I'm going to one more time, I'm going to copy, all of my entire mathematical expression. One more time, I'm going to copy these values. And the only difference is that this time I'm going to very slightly nudge A by H. And then we're going to say L2 is equal to L dot data. And then finally, last time, we're going to have to do this L2 minus L1 divided by H. That's our slope, right? Boom, 6, right? So we're exactly right, right? So yes, Ganesh, that's exactly right. In our chain that we've drawn over here, and I'm going to fill out these gradients. A dot grad is equal to 6.0. Let me just do B really quickly. So instead of slightly tweaking A, let's slightly tweak B. B dot data plus equals H. We get -4. Awesome. B dot grad is equal to -4. Look at that, guys. Now if I draw a dot of L, boom, my entire graph is filled out. So Ganesh, to answer your question, the gradient in each of these boxes represents what is the slope or what is the derivative of L, the final loss function, with respect to each of these values. So for example, we would expect that if I doubled A, what should be the effect on my output? I'm going to ask that question for the chat, everyone. If I double A, what should be the multiple that L is changed by? Any guesses? 12. There we go. Boom, right? If I double it, that's times 2. Take the gradient, multiply by 6. Easy peasy, right? So this is the question we're trying to solve, is how do small variations in our input influence our output? All right. Now I'm going to put this in terms of multivariable calculus. If you guys remember, we're basically constructing a multivariable equation, right? Our equation over here is L, and each of these leaf nodes are our input. So A, B, C, and F, these are our inputs. So remember, in multivariable calculus, we learned that when we have a function like this one is, which is, A times B plus C plus F, right? Or sorry, in this case, it's A times B, what's it called, plus C multiplied by F, right? That function is going to be A times B times B plus C times F, right? This is going to be a multivariable equation that is a function of A, B, C, and F. And if we were to derive this, when we derive a multivariate equation, we end up with a gradient vector, right? So if I have, for example, the input, which is A, comma, B, comma, C, comma, F, right? And let's say our function takes A, B, C, F as input, and it returns L, right? That's what we're doing right here. We're taking in four inputs, in this case, A over here, B over here, each of these leaf nodes, and we're returning one final scalar value, which is L. If we are to derive this function, so if we do dl with respect to each of these things, I'm going to use the gradient operator. Gradient is an upside down triangle. So if you guys see this, see that upside down triangle right there? Excuse me, let me use a raw right there. That is going to be a vector whose elements are dl with respect to dA, dl with respect to dB, dl with respect to dC. Do you guys understand what I'm doing here? The gradient vector is defined as a vector whose each element represents how do small changes in that input affect the overall output. That's a gradient, right? So when I have a multivariable space, instead of a two-dimensional graph, I have this kind of, multiple dimension space. And when I take that vector ABCF, the gradient vector is for each of the elements. How do small variations in that element affect the output? So the derivative of each of our values is the gradient vector. All right. All right, perfect. All right, guys, just stick with me a little bit longer. We're almost at the halfway point, and we're going to take a break, I promise. But we're getting to the really cool part. The really cool part is this. Let's print L.data right now. It's -8. How do I do, what can I do that will guarantee increase this value? Well, we know from multivariate calculus that if I have a point in, whatever dimensional space, and I add the gradient is the direction of steepest ascent, right? So I'm going to prove that for you very quickly with like Desmos. Let's say if I have a function x squared, right? The gradient at, for example, this point is going to be equal to 2 times x, right? So in this case, the slope is 4, right? We know that if I'm going to take my x and if I add the gradient, that's always going to be the direction of steepest ascent. It's going to increase my values. Let me show you what that looks like in practice. Let's say, for example, I have L.data, and if I take, my vector ABCF, which is 2, -3, -2, 4, right? Let's increase each of those values by the gradient. Okay, let's just do like a really small multiplication. So let's do that for A. Let's do it for B. Let's do it for C. Hopefully you guys see what's about to come out here. Gotta put the multiplication right there. Sorry, guys. F.data, F.grad. Okay, guys, you see what we're doing right here? We're taking our values, A, B, C, and F, and we're adding the derivative of the loss function with respect to each of the values and just slightly nudging it in the direction of the gradient. Now, who wants to guess? Is L going to increase or is L going to decrease? Very quick in the chat, increase. Obviously, the gradient is the direction of steepest ascent. So now if we recalculate, remember L is equal to A times B plus C right here plus F, sorry, times F. If we calculate this one more time, I'm just gonna chuck the function in there. And then if we one more time print L.data, boom, -7.92, right? So hopefully you now see that if I take these multivariate equations, if I determine their derivatives, and if I add to their values the gradient function, I can increase whatever the output is. This property is super useful. And the reason is that if I build these long computational graphs of neural networks that are composed of all these neurons, and if I can understand how does each tiny weight affect the output, then I can make a function called a loss function, and I can determine how do I tweak each one of my weights such that I will decrease my loss, right? So I can decrease or increase, whichever direction I want to go in. All right, so you can see L became less than negative, so it increased. All right, cool. Now you're probably thinking, all right, Saad, you've used this word neural network a bajillion times. Please tell us what is a neural network, right? A neural network looks exactly like this. So if I'm going to search up CS231N neuron, I love this image right here. Google's going to load. Just one second, guys. Fazan, I'll give it back to you in just one second. A neural network is a simulation of the brain's neurons, right? So basically, what is a neuron? We have these neurons in our brains that are basically taking input signal from their synapses, right? So neurons are like, linked together, and there's all these different neurons that are, giving in signal into the neuron. And all of that data is going into the neuron, and the neuron is firing it down the axon terminal, and then it's going to the output, right? So if I were to visualize this, it looks exactly like this. I have a bunch of inputs, and what an individual neuron does is it multiplies each of those inputs by a weight. It adds them together. It adds a bias. We can think of bias as trigger happiness. Even if all of our inputs were zero, how much would the neuron like to fire? That's our bias. And you can see that's a linear operator right here, taking all of the inputs, multiplying them by a weight, adding them to a bias. And then finally, we run what's called an activation function. Activation functions are basically nonlinearity. So let me give you a very classic activation function. This is called tan of h. Tan of h takes whatever input it has and it squashes it in between -1 and 1. And this is the most basic theory of neural networks, that a neural network that is composed of enough neurons and enough layers, provided it has a linearity and a nonlinearity, like tan of h over here, it should be able to approximate any function, no matter how squiggly or ugly it is, right? We're going to go after the break. We're going to take a brief 1 minute intercession. Now that we're able to basically multiply and add numbers and get gradients, we're going to talk about, okay, how do we build one neuron? Then how do we build one layer of a neuron? And finally, how do we make our multi-layer perceptron? But I'm going to go ahead and pause so Fazan can talk.
Amazing. Thank you so much, Saad. And hopefully all of you are able to follow along and come understand what he's going over. So just want to take a quick kind of intermission here. So we at Head Starter, we have been traveling quite a lot. We've been going to different cities, different kind of college campuses. And most recently, we were in University of Waterloo in Canada. This was last weekend when it was like a super bad snowstorm. And Yassine, my co-founder, he posted that we're going to be at Waterloo. And within 12 hours, we got over like 100 people to come to our meetup at the engineering school in University of Waterloo. And in that meetup, we got to meet so many, amazing folks. Everyone there is super smart, super, driven, and I hope to see more of them come to SF to build. And particularly, there were these two students that we met, and I'm going to invite them to come speak right now. Uh, their names are Akshat and Malhar. So they both are building something that's quite interesting. And Saad, I want you to also ask them a couple questions. But they're building a startup that is essentially like Git for ML models. So it's pretty relevant to kind of what we're doing here today. And I want them to actually demo to you all what they're building because I think it has a lot of potential. So Akshat and Malhar, please take it away.
Hey guys, can y'all hear me?
Yep.
Hello. Can you guys hear me too?
Yeah, we can.
Okay. Hi, so everyone, my name is Mohar.
And I'm Akshat. Huge thanks to Faison for letting us do this. Me and Mahar have been working on something called Gradient, something that you probably heard a lot throughout this lecture, actually. And to give you guys a bit of background about ourselves, I'm a junior studying computer science at the University of Waterloo. In the past, I've worked as a software engineer at a Series C startup. I've worked at AWS as a software engineering intern on network infrastructure. And this summer, I'll also be going to Databricks to work on ML infra, which is actually very similar to the product that we're building out.
Yeah, and as for myself, I'm a senior studying computer science at the University of Waterloo. Previously, I've interned at Amazon AGI, which is their artificial general intelligence team, and I've also worked at Meta on their ML teams for Instagram Explorer. And this summer, I'll be joining IMC Trading as a software engineering intern.
And that brings us to our product. What is Gradient? Well, Gradient is pretty much an infra tool that brings Git, and I'm sure you've all heard of Git and GitHub. We bring this version control semantic to machine learning training, specifically for checkpoints. So allowing branching, forks, and deterministic resumes. And at the same time, we've developed a way to minimize storage costs with anchor and delta checkpointing. Now, speaking more to the version control aspect, it allows users to organize these repositories organize their branches into repositories and workspaces, which allows for a much cleaner and less wasteful model training workflow, both in terms of time as well as cost. And I'll pass it on to Malhar to talk about how we actually came up with this idea and then actually demo it as well.
Yeah, so I initially came up with this idea when kind of I faced the problem at Meta when all the basically models I was working on, let's say a model didn't work out, I would have to retrain the model and it would essentially waste like a bunch of days of compute. And so I thought, why isn't there like a simple version control layer just as there is for like normal software engineering? And so that's kind of how the idea was born. And so I'll just give a really quick demo of how it works by sharing my screen here. Can you guys see my screen?
Yep.
Okay.
Yep.
So all you have to do is Gradient, as of now, is just a Python package that you can pip install, like you pip install any kind of Python package. So, and I already have it installed, so it'll be pretty quick. So how it works is actually quite simple. Essentially, what you do is you first have to create a workspace and a repository. It's basically, you can think of it as a repository in GitHub. So I can do gradient workspace in it, and we'll call it experiments. And what this will do is it'll essentially just create a workspace that we can work under. So let's go into this workspace and we'll create a repository for basically all of our ML workflows. So let's look at this first workflow we have here called train.py. It's just a really kind of small model that we have defined in models.py. It's just 2 layers and with its own activation function, as we just talked about. Okay. So if I go back, all we have to do is we have to attach the gradient engine to the model and the optimizer. And what it'll do is it'll essentially auto commit every, say, n steps. Here we chose n to be 5. And this will allow you to go back to any point in the past and commit from that point. So let's just create the repository. So gradient repo in it. We'll call it tiny MLP, just name it after the model. Tiny MLP. And we'll give it a description of this is my tiny MLP. So once this repository is created, what we can do is we can then run this train.py file. And we'll see that it'll auto commit. And for just kind of this demo, we have only done up to 20 steps. But as you can see, if I make this a bit bigger, we'll be able to see that we're saving a checkpoint every 5 steps. And so if I go back into our workspace, we can run basically similar to how you run git status. You can do gradient workspace status, and this will allow you to see your repository and the current kind of state of it. So as you can see, this is our tiny MLP repository, which has 4 checkpoints, and it has currently 1 branch, which is the main branch, which is currently on step 20. So now if I go back, what we also allow you to do is to fork. So let's say I got one of the parameters of my model wrong, and for this tiny MLP model, and I want to increase the learning rate from 10 to the -3 to 10 to the -2. All I have to do is I just have to specify that I want to be on another branch, and I have to specify where I want to fork from. in this case, I'll fork from the main branch at step 10. So now if I run train.fork, we'll see that in the output, we will resume from step 10 up till step 20 with a new learning rate. So, or up to step 25, I guess, is what is defined in the file. And now if we go back into our workspace, we'll see that the repository will actually save both pieces of information. So kind of helping you organize the branches that you currently have. So now we'll have our high learning rate branch, which is at step 25, and our main branch, which is at step 20. And just quickly, the last function I kind of want to show you guys is, let's say we want to train another model entirely. And that would be like a kind of larger model called deeper MLP. We can do that as well. All we have to do is initialize another repository in the same workspace called deeper MLP. So let's run this file. And we'll see that if we go back into our workspace, it'll be another repository with the second model. And so for this one, I specified that I want to commit at every 3 steps, and I went up to 30, like a total step size of 30. And so going back into the experiments, we can again look at the status, and there'll be another repository created for this second model. I can give it back to you, Akshay.
Cool. Yeah, I think we're gonna have to stop there, unfortunately. But so Akshat and Malhar, Saad actually has a couple of questions for you both, and
Yeah,
Saad.
gentlemen, I love this. This is amazing. So both at my time at Tesla and Essential, this was a problem that we ran into all the time, especially when I was at Essential. We were working on AMD GPUs, and for a million reasons or the other, we would have hardware instability, and frequently the training runs would stop and start and stop and start and stop and start. Right. So I guess I have a couple of questions. I guess, what do you see the main use case for the feature of multiple branches? Is the idea there that we're testing multiple architectures in parallel, or why would someone want multiple, or for example, different configs? Yeah.
Akshay, do you want to take it? Or
Yeah, sure. I think there's many use cases. I think one of the first use cases we started off with was, let's say you had like a bad piece of data that came in at a specific batch later on in your model, right? So the initial intention there was to be able to go back to a specific checkpoint, branch off from there, and train on your updated data, right? While also like keeping track of both of those pathways. And then another approach that we sort of came up with along the way was what we showed in the demo. For example, at some specific point, maybe you want to
Mhm.
test out a different learning rate, or you want to change your hyperparameters. Maybe you want to reset your optimizer at this specific point, right? I feel like there's so many use cases in that situation. And that's sort of where we see this being used. I think it'd also be very useful for independent researchers, not just corporate.
Awesome. Excellent. And I love that you talked about as well, learning rates, because that's something that, we ran into all the time where, our first, let's say 10,000 or a million steps or however many epochs we're doing in the beginning, obviously we're gonna have a very high learning rate. And then we
Exactly.
sometimes want to branch and see, okay, how does it compare if we maintain the same learning rate, if we have a very different learning rate, especially, and we're going to talk about this later on in the class, obviously now we're just in lecture 1, but, there's different approaches where you can kind of linearly scale down your learning rate. You can have it in more, like sine kind of way, but I love it. Okay, let me ask you, how does this turn into a business? How do we make money off of this?
Mahar, you want to take that one?
yeah, for sure. So now that we've kind of identified that there is kind of a issue, there's like a few kind of strategies. So firstly, we kind of want to make this open market for like individual users, right? So because teams train fine-tune models weekly, running like just spot experiments, doing lots of branching, etc. And so that kind of tool we want to make open source. And then when we
Mhm.
want to kind of convert that to a business, that's when we get into kind of making other actual companies, say like startups that are actually training their in-house models to actually start using Gradient. And we would help provide them the storage for the checkpoints and kind of any support that they would need. similar to how GitHub and like GitHub Enterprise works.
Awesome. That's excellent. No, I love that model. And I think especially for small teams that are training models, being able to chuck your checkpoints onto some kind of cloud platform and kind of visualize those would be very, very helpful. So great work, gentlemen. This is amazing.
Yeah, and I just wanted to make a quick mention. I'm gonna drop a link to our waitlist actually. So everyone who's interested can sign up for it. Um, and I'll also add a link to a YouTube video, which is a longer demo, much longer, it's like 7 minutes long, that shows a few more of the features we have. And stuff that you guys should look out for is we are going to have this integrated for distributed training. Training, as you guys know, is not just on one GPU anymore. Models get huge. So we're adding integrations for FSDP, which is fully sharded data parallel. We're also adding integrations for um, deep speed as well, which is Microsoft's way of doing distributed training. So you guys should look out for that. Lots of cool stuff to come. I've put in the link to the waitlist. I'll also add a link to the YouTube video. And yeah, everyone sign up. And when we go, I guess, publish this package and you guys can use it, all of you guys will be the first people to hear about it.
Awesome. Thank you guys so much, gentlemen. I appreciate it.
Amazing.
Guys,
Thank you so
I'm
much,
going
guys.
to go ahead and share my screen and we can kind of get back into it. And then afterwards, we'll have enough time for questions. Is that cool, Faizan?
Yeah, go ahead.
Okay,
I just
perfect.
want to share,
So
so Akshay and Malhar, they, are deep into ML. They did ML in their internships, and now they turn it into a business. So I hope all of you are inspired by the work that Saad is doing here, and you pursue something maybe of your own or at a company, based on what you learn here.
awesome. Let's get into it. Yeah, and I love the concepts that Maher was talking about like fully sharded data parallel, all that kind of stuff, because we're going to get into all of those things. And just a brief note on what that means. Right now, we're going to train our neural net on my MacBook on one machine. But in the future and in production systems, when you train GPT-5, even GPT-2, you're training on not one machine, you're training on thousands of machines that are distributed across the world, that are each running forwards and backwards passes, that are sharing their gradients. So these become very complicated systems very quickly. But let's stay simple for now. Like I said, today's just lecture one. We're going to have a long road ahead of us until we build GPT-2. Let's go back to, again, what is a neural network, right? So again, neural network is a collection of neurons that are arranged in a layer. Multiple layers compose a neural network, and each neuron has basically inputs that come from synapses. These inputs can be like x0, x1, x2. Each of these inputs, we perform a linear function on them. So that means we multiply each input by a weight, add that up, add that to a bias that represents how trigger happy the neuron is. You can see right here, let's say all of our inputs were zero. 0 times all of our weights is 0. So just the bias is going to be left over. So the bias is saying this particular neuron, how trigger happy is it? How much does it like to fire even if we don't do anything? And then finally, we apply that nonlinearity. And the key principle here is if you have a linear layer followed by a nonlinear layer, linear, nonlinear, linear, nonlinear, you can approximate any function. And the ability to approximate any function means that any given group of inputs to any given group of outputs, you can train a model off of that, right? So is everyone with my English description so far, right? Everyone's good with that? Cool. Let's go ahead and build this. Let's make a single neuron. I'm going to import the random class just so we can get random, numbers right here. Let me get a little bit of extra cells. Let's make a class. Let's call it neuron. This neuron, we are going to, actually, just one second, guys. Before we get to that, I actually want to add a bit more functionality before we go ahead and do the neurons and everything like that. I want to make sure we can do both multiplication and division, but that process that we walked through of doing the back propagation, I want to make sure we can do that automatically because that was like really finicky, right? Where like we had to calculate by hand every single node and how it related to every single input node, right? So we're going to actually go back just slightly, and we are going to clean up our value class. Okay, so now let's actually implement our backpropagation algorithm. So let me grab our value class, which is all the way up here, right? Super basic so far. It's got a gradient, it adds, and it multiplies, right? Let's move on to the next step, which is let's have a function called backwards. Backwards on the first node is going to be very basic. It's going to be a lambda function that does literally nothing. But the idea here is that that step that I walked you guys through manually, where we went through every single, node at the end, and we said, okay, how does this output node relate to each of its input nodes? We want the backward function to do that automatically, right? So for the base case, the function is going to do nothing. But let's say, for example, we have the add function. For the add function, I want to implement backwards right over here, which is, for now, I'll have it do nothing. But the idea here is that when two values are added and that output is created, when somebody calls the backward function on the output, we want something to happen that propagates information all the way down to the inputs. So we're going to use, some functional programming right here. If we set out dot backward is equal to backward, what this is going to do is that when we have a plus b, right? If I got a plus b over here, and that's equal to c, c dot backward is going to be this inner nested function right here. This is really key. The reason we're going to use nested functions here is because when we do that backward operation, remember I told you guys that when you do backpropagation, what's most relevant is your given node and the input nodes. Well, the great thing is that we have access to all that data here. So if we're doing a plus b equals c, we know that this one is really straightforward, right? We want to be able to take our input nodes and change their gradients. Self.grad is equal to 1, right? Same thing, other.grad is equal to 1. The only difference here, remember, guys, we can't stop here because this is just the base case if we have like c is equal to a times b. But if, for example, c is equal to a plus b, if we had a more nested function, remember, like I said, we want to multiply by the output gradient. So this is the concept where we start at the very end of our directed acyclic graph and we propagate all the way downward. So I'm going to go to my chain rule right over here. Remember, guys, what we did is that we said, for L, if we want to figure out what its gradient is with respect to D and F, that's pretty straightforward, right? Like we just did -2 and 4. But once we went one layer lower, when we were trying to figure out what the derivatives were, what the gradient for E and C was, the two numbers that were the most relevant was what's the operation that we're doing right now, E plus C. And remember, when you derive addition, it's as simple as the gradient is just 1, but you have to multiply it by the output gradient. See, the way that we got -2 here is that we're multiplying 1 by -2 right here. So now we're going to kind of go back to our value function all the way up here. Where is it? And we're going to say, okay, take our gradients. The gradient when you do an addition is just 1 and multiply it by the outward gradient. That's it. That's all it takes, right? Same thing for multiplication. Multiplication is super straightforward. Def backwards function right here. We're going to say self.grad and we're going to say out.grad. Okay, so when we're multiplying two numbers, what is its what's it called? What is the gradient? Again, if I'm doing C is equal to A times B, right? And if I want to say what's DC with respect to DA, it's B, right? So self.grad is going to be other.data. And again, we're going to multiply it by out.grad. Same thing over here. Self.data multiplied by out.grad. Now, this is a really key point here. So I'm going to stop for a second. I'm going to allow everyone to really visualize this. But can everyone understand why do we want to propagate? Like, what is kind of going on here? So Edward Tran, for example, is asking, what does out.grad mean? Remember, in our value function, if we're in the multiplication world, let's say we're doing A times B. C is what out is. A is self, and B is other, right? So when we do C is equal to A plus B, we're going to go into this multiplication function. A, self is basically going to be A, right? Other is going to be B, right? And we're going to construct this new thing C, which is out, right? So what we're trying to figure out when we do the backwards function is as we backpropagate every single node, what are the gradients for each of the inputs? So in this case, when we backpropagate C, the gradient for A for multiplication is going to be B. It's going to be other thing, right? So that's why self.gradient is other.data. But the reason we had to multiply by out.grad is that whenever we're working with, I don't know, a long directed acyclic graph like this, and we're all the way down here at B, right? The gradient for B in this case is going to be A. It's going to be the value of A, which is 2 right there, multiplied by the derivative of L with respect to E. So that's E's gradient right there, in this case, out.grad. All right, so hopefully that makes sense. We're going to kind of chug along. So now we have our backwards functions all implemented. I also told you guys about nonlinearity. Let's go ahead and implement a tan H as well. I think that would be pretty useful, right? Tan H is this function that I have all the way down here, which is a nonlinearity, right? So let's Google what the hell is tan H. Let's do tan H Wikipedia. Okay, hyperbolic functions comes up. Boom, look at that. Tan H is defined as e to the 2x minus 1 divided by e to the 2x plus 1. Cool, that should be pretty straightforward to implement. So let me go back to the value class. And let's make our tan H function. I'm going to say, let's say x is our data. And I'm going to just use an intermediate variable called t. And then I'm going to say e to the power of 2 times x. Let me just split this left so you all can see. You guys see, I'm literally just copying this function right here, right? So e to the power of 2 times x minus 1. We're going to divide that by e to the power of 2 times x plus 1. Boom, that's the tan function, as simple as that. And again, we're going to have a value, a t. What's the child of tan H? Well, tan H only takes in 1 input, so it's just going to be self. And then we're going to label it as tan H, right? Boom, pretty straightforward right there. Return out. Okay, awesome. Let's just Google what is the derivative of tan H. Wow, that looks kind of crazy. Let's go in images and look at that. The derivative of tan H is 1 minus tan H squared, right? So it's, okay, that's pretty simple to calculate. Let's do that as well. So if we have a backwards function and we say self.grad is 1 minus, and remember this thing was tan H right here. That's our data. So t squared, right? Multiplied by out.grad. Boom. That is the derivative of the tan H function. Okay. So now we have a pretty powerful value class in just a couple lines of code. So I'm going to, for example, let's come up with some crazy arithmetic that we can test this thing out on. So I'm going to run that cell and go all the way down here to neural network. Sorry, guys. Let me just copy paste this giant blob of text. Forgive me, guys. Chuck this all the way at the bottom. Sorry, I'm scrolling a lot. So boom, that's our value class. Let's take some examples. So let's say I've got some inputs. We're going to have inputs x1 and x2. Okay, these are going to be values 2 and 0. Let's have some weights. We're going to have some weights -3 and -1. Boom, those are our weights. Let's multiply our weights by our, what's it called? Our data. So that's x1 times w1. I'm going to call that x1 w1. Let's also have a bias. Guys, ignore the ugly value of the bias. I picked this bias for a very specific reason. It's going to make our gradients very simple, but it's a really ugly number. But I could have picked anything. And then finally, we're going to say, okay, x1 w1 plus x2 w2, right? So that's the linearity right there. Add the bias, and then finally, we're going to call that value n. So n, guys, I'm literally just taking. If I go to CS, 231, the definition of a neuron. I love this image so much. I'm literally just re-implementing this image right there, right? So I'm taking, in this case, our neuron has 2 inputs that are getting multiplied by 2 weights that are getting added by the bias. If anyone's curious why I'm picking such an ugly number for the bias, I just made it up. So forgive me. It's just this particular number ends up making it really nice when I graph it later on, but I could have picked anything. I just wanted the numbers to be all, what's it called? Whole numbers. Cool. So now let's, multiply. We have multiplied the weights by their data. Let's add them up. Let's add the bias. Let's apply the nonlinearity. And let's see what the hell comes out. So let me also do O dot label is equal to O. If I didn't make any silly mistakes, that will code correctly. Let's draw dot of O. Boom. Hey, it's our first neuron. Our first neuron takes in data, x1 and x2. It multiplies them by their weights. It adds those two together. It adds a bias. That's an n. It applies tan of h. And then, boom, there you go. I want to show you guys just tan of h in practice just one more second. So remember I said that tan of h is a function that takes whatever input it has and it squeezes it in between -1 and 1. So guys, check this out. If I change the bias to be like, I don't know, like some giant number, that's a big number right there, right? Okay, hold on. Okay, it's too big. Let's do like 200, right? Pretty big number. Bias is 200. Now the data is 194. And look, tan of h, it got squeezed to 1, right? So that's the beauty of tan of h, is that whatever the input or output is, it squeezes it to -1 or 1. That's our nonlinearity right there. Let's go back to the magic number I picked before. All right. If you chose the bias, how do you determine the right bias, or is it just random? Great question, Haris. This is the whole point of machine learning, which is how do we figure out what should our weights be and what should our bias be? That way, our function actually produces sensible output. And that's a process called training a neural network, where we determine what are the best weights and what are the best biases that give us a neural network that produces a model that fits our data. We're going to train the neural network in just a second, but let me just finish actually building it. Cool. So this is one neuron that we've got right there. Why don't we visualize this? Okay, boom, I visualized it. You'll see right now all the gradients are empty. 0, 0, 0, 0, 0. So I haven't really, called my backward function. So that's expected. Let's go ahead and do that. So let's say O.grad is 1.0, and let's call O.backwards. Let's run that. I need to do draw dot of O again, and you'll see, you guys just gotta trust me on this one, that the gradient is 0.5. So now you guys can see the reason why I picked that really ugly number, because it made a really simple gradient. Again, remember guys, the derivative of tan of h is 1 minus tan of h squared. So if I was to do 0.7071 multiplied by 0.7071, that is 0.5, right? So 1 minus 0.5 is 0.5. All right, is everyone with me so far on how we're able to run O.backward on that final node and get, if I can just get a yes in the chat, everyone understands? Real fast. Okay, perfect, cool. So now we did one backwards pass of just one node, all right? Let's keep going. Let's see how far can we run this thing. Now let's do n.backwards, right? So what is n? N is the result of adding two numbers. If I add two numbers, I know the derivative is 1. And when I multiply by the gradient, because remember chain rule tells me that if I want to understand how is this node x1 w1 plus x2 w2, how does it affect the output? I have to understand its local derivative, which is 1, multiplied by the gradient that's getting pushed in, which in this case is 0.5. So boom, let's run n.backwards. Let's do draw dot of O. Hey, look at that. 0.5 got propagated to each of these input values. Okay, cool. One more time. Let's do it one more time. Now let's do b.backwards. Now, b.backwards doesn't really do anything. B doesn't have any inputs. So it's that, lambda none function is getting run. So that does nothing. Let's do x1, w1, x2, w2 dot backward. This is, the really cool one, because it's another addition that's, going right here. And let me run that thing. Let me one more time do draw dot of O. So previously these gradients are 0. Look at that. Now they're 0.5. Why are they 0.5? Same thing. We're taking the gradient that's coming in from the layer above, 0.5. We're multiplying it by the local derivative, which in this case is 1. So it's just propagating downward. See why we call it back propagation, right? All right. Last time, I promise, we're going to take each of these values, x1, w1, x2, w2, run the backwards thing. We are going to draw one last time what this looks like, and boom, there you go. Now, even I have this neuron, which looked really simple when I did this like stupid little image right here, but it's like, I can see that x1, if I double x1, I have to take -1.5 and multiply by 2, right? I can see how do small changes in my data, and more importantly, how do small changes in my weights influence the final output. So what's really cool here is W1 has a gradient of 0. No matter what you do to W1, no matter if you adjust your weight by a bajillion, right? You're not going to affect your loss output at all. This is a really bad thing. We're going to talk about in later lectures, how do we make sure that the gradients are not ending up at 0 and is basically making these weights useless, right? Because this is a useless weight. No matter how much we change it, it's not going to change the output. Cool. Let's keep going. Now you guys are thinking, Saad, that was really freaking tedious. You had us do the backwards function on every single node. Is there any way that we can just like automatically do it? Does anyone know the name of the algorithm that takes a directed acyclic graph and sorts it in an order such that input nodes are always behind output nodes? So for example, Huffman sort, yes, boom, Ganesh is right. Topological sort. Topological sort is the algorithm where if I were to topo sort this graph, it would return an output that made sure that any intermediate node that depended on a previous input, the inputs would come first, right? So let's do topological sort. You guys think that topological sort is only used for leak code problems to punish you? No, it's also used in machine learning. So let's make a function called build topological sort. Again, we're going to have a list. That's our output. What is the actual sorting? And we're going to have a visited set, right? What are all the stuff that we visited? Well, what's the topological sort algorithm? For each vertex, we say, hey, only if we haven't already visited this thing, if V is not in visited, then we want to add it to our visited set, mark it that we're looking at this node. And then we're going to say for each of the children in this node, so V dot prev, we want to call topological sort on that, right? And then once we have exhausted all the children, once we've recursed and recursed and recursed, and now this for loop is returning nothing. So for example, let's say we're at a leaf node like B. This for loop is going to do nothing, right? There's no children that B has. Then, okay, cool. Let's go ahead and add that node to our topological list. All right, cool. Let's do build topo on O and see what comes out. What the heck did I do? Oh, call the topo thing. Sorry, my bad, guys. So there you go, right? So there's our topologically sorted thing. So you can see that, for example, the node that has data of 0, which is x2, then it's the node that has data. This is x2. So this is doing x2, w2, right? So where it's starting with those two, right? Then it's going to x2 times w2. Then it's saying, all right, here's w1, here's x1, here's w1 times x1, right? So as you can see, we've topologically sorted it. The order is such that we're beginning with all of our inputs. And why did I have us do topological sort? Because I wanted to have an automatic function where I could call backwards on all the nodes in the right order. Remember, if I call backwards on the inputs first, it's not going to make any sense because in our function, we have to propagate that gradient all the way downwards. So guess what we're going to do? We're going to say for each node in reversed is a function in Python that if I have a list 1, 2, 3, 1, 2, 3, and I call reversed on it, boom, it does 3, 2, 1. Let's do for each x in, right? Boom, it does 3, 2, 1, right? I had to burn a list comprehension. Cool. If I do reversed of the topological sort and I do node dot backwards, there we go. Now I have successfully called it automatically and I get the same result right there. Okay, this is getting really powerful, right? Because now I can take my value class. Somebody is asking, is this a static computation graph? Yes, this is a static computation graph in the sense that all the weights are basically fixed, right? Like we're not changing anything. Okay, let's go ahead and take my value class and let's add a function called backwards. And let's basically just re-implement this super fast, right? So same thing, I got my topological list, I got my visited set, I've got my function build topo. I'm just copying this from the top here up here. Same thing if V is not in visited. Actually, let me just copy this. This is getting inefficient. Boom, just copy that right there. So there's the topological list. There's the visited set. Let's make my indentation a little bit prettier. If a given vertex is not in visited, oh, sorry, I have to tab one more time. There we go. So we're going to build a topological, instead of calling on O, we're going to call it on self. So this is going to be, called on a given node. We're going to build a topological set from that node. One small thing we have to do, guys, is we have to initialize the gradient. You'll see that I left it as 0. That was very purposeful. It just makes it really easy to when we kind of update with multiple nodes later. But we want to make sure that when we call backwards on a given node, we're basically saying, all right, what is the derivative of all what, how do all of these inputs affect the output? And the output, of course, is just going to have a derivative of 1. And then finally, we're going to go in that reversed order of the topological sort, and we are going to call backwards. Cool. So now let's take this one more time. I'm just going to copy paste the function x1, x2, w1, w2. See that? And now what I'm going to do is, so again, this is an empty. See, all gradients are empty. Everything is 0, 0, 0, 0, 0. Now I'm going to call, look at this, it's going to be so powerful. O dot backwards, boom. And now when I call draw dot, everything is filled in, right? This is amazing. We have built a successful autograd engine. Maybe there's actually a couple bugs. Let's talk about the bugs. Let's say I have, is everything clear so far? Yeah, Haris, everything is good? Okay, cool. Let's talk about an example. There's a bug that's in here. If anyone can catch it, I'll be very impressed about how we're calculating our gradients. But if no one knows it yet, I'm just gonna go ahead and talk. So let's say I have the value a, which is 3. And let's say I have a function, which is a plus a. So in math, we would call this b is equal to 2 times a, right? Let's call, b dot label is equal to b. Let's go ahead and call b dot backwards on this. Let me quickly draw. Actually, before I do the gradients, let me just draw this first. So you'll see, sorry guys, the two nodes are right on, they're stacked on top of each other. That's why you're only seeing one A. There are actually two A's here that we're adding. Forgive me, they're just on top of each other. And that's the exact bug that we have here, which is that when we have values that are the same, look, the gradient is going to be wrong. So guys, first guess, what should the gradient be here? If I have B is equal to 2 times A, what's the gradient of A? Really quickly here, guys, if B is equal to 2 times A, yes, 2. Okay, cool. So now let's call B dot backwards. And what do I get? Oh no, I get 1. So I need to now Google chain rule Wikipedia. I need to go all the way down to, sorry guys. I need to go all the way down to multivariate, multivar. Okay, we can see here when I read this complicated, stupid looking math, that when I have a chain rule of multiple input functions, I need to add up all the inputs. That's the bug right there. So what's happening is when I go to my value class and when oh, screen sharing stopped. Thank you guys. Sorry. I'm so sorry. Just 1 second, guys. Okay, so I'm gonna backtrack. So again, the bug here was that I had this function 2 times a, and I got the gradient as 1, when that's obviously incorrect, right? If I have a function that is b is equal to 2 times a, the gradient should be 2, not 1. And what's going on here, guys, you can see my screen now, right? We're good? Yes, okay, let's keep going back, scroll back up. What's happening is that when I have my add function, when I do b is equal to a plus a, self.grad is being set to 1 here. Other.grad is being set here. And again, when backwards it's called, it's running it the backwards function on each of the children nodes. So what's happening is that one value is getting overwritten. First, the gradient, which is a, this is a.grad, is being getting set as 1. And then again, other, which is also a, right? Because we're doing a plus a, is getting set as 1. So this is incorrect. What we should do is not equals, but plus equals, right? So that's what Wikipedia is telling us here with that sum, that when you have these gradients, they add. They don't simply, overwrite each other. So I'm just going to fix that right here. Plus equals, same thing, plus equals, right? So now if I run this thing, let me go over here. Boom, there we go. The gradient is 2, right? Okay. Was it rewriting something? Yes, Nicola, you're exactly right. It was rewriting over itself. That's right. Yeah, so the gradient is kind of like a counter. Okay, I want to do a little bit of code cleanup. We're almost there, guys, almost at the end. But let's make this, a little bit more production class. First thing I want to do is I want to add RMUL. So you'll notice if I have, for example, actually, let's do something even simpler than that. If I have this value class, and if I do, let's say, value of, let's say 1, right? That's A. If I do A plus 2, it's like freaking out, right? So why is it freaking out? Because it doesn't know, Python doesn't know how to add an int with a value class. No biggie. That's super easy to fix. We're going to go to our other function, and we're going to say, hey, okay, if other. So if it is an instance of the value class, no biggie. We're just going to say other is equal to, actually, let me keep this. Other is equal to other, right? This is a one-line if statement. Forgive me for making it a little bit ugly. But if other is an instance of value, just give me other. But anything else, if it's a float, if it's an instance, whatever, just wrap that thing right there. So if I put this line right here, now when I add a plus 2, you can see we're totally fine, right? I'm going to do the same thing with multiply. So, we're able to multiply these numbers. And then there's another problem. If I do 2 plus a, it doesn't know how to do 2 because it's trying to go to 2's add function and it doesn't know what to do. So this is just a little hack, guys. There's a function in the language called radd. And basically what it says is that if I'm doing 2 plus a, Python says, okay, if 2 plus a fails, is there any chance that a plus 2 will succeed? So it will call radd on the other operator. So all we have to do to implement radd is return the result of, if I have self plus other, boom, self plus other right there. What did I do? A is equal to value 3.0. And if I do 2 plus a, you can see that works. So 2 plus a works. And if I do, same thing, a plus 2, that works, right? We can implement the exact same function for our mul. So now I can do, 2 times a or a times 2, no problem there. All right. So sorry, just a little bit of code cleanup right there. One more thing, I want to make sure that, so our tanh function is implemented pretty well. Let's also do the exponential function. I think that will be pretty nice. Let me just grab one thing really quickly. All right, guys, just one sec. Okay, so we've done add, we've done multiply, we've done tanh. Now let's do pow, right? So pow is basically if I have, some given value x and I want to square it, right? The reason why power is very powerful is it'll also help us do division. So you'll notice we haven't done division so far. So a divided by b is actually the same thing as a multiplied by 1 over b. And that's the same thing as a multiplied by b to the power of -1, right? So some basic math right here. If we're able to do exponents, then we can even do division, right? Because division is just a fancy case of multiplication and power, right? So let's add that right here. First, we're going to go ahead and we're going to do power. So let's just check that right here. Pow. And if I do self and an other, so in this case, self will be, my value, and then my other is going to be, let's say if it's 2, I'm squaring it. If it's 3, I'm cubing it, right? We're going to do the same thing. I want to make sure that for now, we only do exponents of integers or floats. We'll get into complex numbers or other stuff later. Yeah, let's do the value. So the value is going to be self.data to the power of other, right? Nothing crazy right there. The children of this operation are just myself, and we are going to call it, we're going to put a little string there that says, okay, are we squaring it? Are we cubing it? What are we doing right there, right? So that's the value right there. Now, if anybody has done, what's it called? Calculus 1, you'll remember there's something called the power rule. The power rule is how do I take the derivative of any power exponent? And it's super simple, right? So if I have x to the power of n, I'm going to drop that n down and I'm going to decrease the power, right? So I'm going to do that exactly here. So I'm going to say self.grad is going to be plus equal, remember, other, that's the exponent, multiplied by self.data to the power of other minus 1. Boom. That's the chain rule. Oh, sorry, that's the power rule, right? And again, we're going to multiply this by out.grad, right? So you can see again how powerful this is in that you're just in a couple lines of code, you're able to bring so many additional functions out dot backwards. I'm definitely going to have some typos. Forgive me, guys. Okay, that's pow. Let's really quickly do now the division. So in Python, it's called trueDiv, which is division, as opposed to floorDiv. Cool. So this is going to be self divided by other. Same thing. All we have to do is return self multiplied by other to the power of -1. See how powerful it is once you have power, right? Okay, cool. The very last one I'm going to implement is exponents. or no, sorry, exponents. Yeah, exponent is going to be e to the power of something, right? So let's say we have x is self.data. Now our out is going to be a value of math.x. This is just taking e to the power of x. Same thing, our children are ourselves. X is our label, and we're going to return that. If we want to have a backwards function, you guys will remember that if I have e to the power of x, the derivative of e to the power of x is e to the power of x, right? So pretty straightforward. Self.grad is increased by out.data. That's e to the power of x multiplied by autograd. Forgive me, guys, I'm going a little bit fast here, but it doesn't really matter. You guys, if you know basic math, you can figure this stuff out. Okay, cool. So now we have a bajillion different inputs and outputs, different functions. I'm going to copy same thing, x1, x2, b, and you'll notice here that where previously we were doing tan of h, I'm going to now do, 2 times n, so e to the 2n minus 1 and e to the 2n plus 1, right? And you'll see we get the exact same thing. Shoot. What did I do? Okay, I need to have a couple more functions. I'm going to just chuck these over here, guys. Just trust me. Negation is times -1. Subtraction is plus times -1. And radd, I think I already put this function here. So let me just fix up my tabbing. There we go. Boom. Okay. So results are exactly the same, right? There's a little bit more complexity because we chose to, not use the tan of h function, but instead write it out as an exponent, right? And yes, guys, for division, you should assert 0, but I'm not going to bother with that right now. Okay, cool. So that's a neuron. How the heck do we do this in PyTorch? Let's do it in PyTorch. Now we're going to do something really fun, which is this is our first time writing PyTorch code. So PyTorch is basically a super advanced version of this where it's using PyC, where the underlying tensors are written as C objects, C and C++ object, which allows us to run very quickly like GPU operations, that kind of stuff. So in PyTorch, we have something called a torch.tensor, which is the same thing as our value class, right? A torch.tensor, we can put a tensor in it, which is a vector. Let's put this number 2. Let's turn it into a double. That basically is just the type. You don't have to worry about that for now. And one thing that you have to do, guys, always remember in PyTorch is that if you want to turn on the autograd functionality, you have to, for each one of your inputs, you have to do x1.requiresgrad equals true. What this code does is it tells PyTorch that anytime this variable x1 is being manipulated, please construct that same computation graph, and please allow me to do backpropagation. So I'm just going to copy paste some code here. This is the exact same thing that we've been working on, x1, x2, but this time, instead of using the value class, we're using PyTorch, and we're using tensors. And for each of the tensors, we're turning on requiresgrad. And you can see this is the exact same operation, x1 times w1, x2 times w2 plus b, do the tan h, torch.tan h is the function we're using here. And now we're going to call, just like we did for our value class, o.backwards, and torch is not defined. Import torch. There we go. The results are exactly, hopefully, kind of the same. 5.824, whatever. Yeah, close enough. I think the numbers are, I had slightly shifted them, but you can kind of see you're doing the exact same thing in PyTorch. So this is the functionality that we've rebuilt. Now let's do the fun part. Let's make a neural net. So a single neuron is defined as it has a set of inputs, right? So we need to know, is our input, for example, so far we've been doing x1 and x2. So we have 2 inputs, right? Of course, that could be anything. But a single neuron is going to have a number of inputs. It's going to have a bunch of weights. So self.w is going to be a bunch of values. For now, let's just keep them random between -1 and 1. Let me make sure I have enough parentheses here. Sorry, guys. Perfect. And then for I in range nin. So what we're doing right here is the number of inputs, we're making that many weight values. And then for the bias, we just need one bias, which is, again, a random number uniform between -1 and 1, right? So that is a neuron. And how do you call the neuron? Well, you have a call function. which is self, and it takes an input. And it literally just does W times X plus B for each of the WXs. Cool, let's implement this. So the action is we're going to do WI times XI for each of the WXI in, we're going to use the zip function right here, self.w comma x, right? So what this is doing right here is basically saying for each of self.w, you guys know what the zip function does, right? Zip function is really cool. If I have x is equal to a list 1, 2, 3, and if I have y is equal to a list 4, 5, 6, zip of x comma y is going to pair all of these together. List of zip. See that? 1, 4, 2, 5, 3, 6. So it's pairing element-wise. So we're going to do that right here. We're going to pair the weights and the input for each of the entries in X, which is a vector. We're going to take that weight, right? And that's going to be WI, and we're going to multiply WI times XI, right? So that's all of our weights. That's going to be a list, right? And then we're going to go ahead and sum that. Okay, cool. Once we sum that, we also want to add to that, what's it called? The bias. So we'll do self.b right there. And what do we do in a neuron? We also have to have a nonlinearity. So action.10h. And we're just going to return that. Okay, so let's see, does this thing actually work? So let me try running that. Closing parentheses does not match on this line. My bad, guys. I need to put a close bracket. So now let's make a neuron. And let's have this neuron have 2 inputs, right? And let's say, okay, so now this neuron has 2 inputs and has a bunch of weights. And let's call this neuron N. And let's do on X. There you go. See, it's random. It's like just taking these random weights and these random biases, and it's multiplying that through, right? So we've made our first neuron. Well, a neural net is not just a neuron, it's a stack of neurons, right? One layer of a neural net is a bunch of these neurons. So let's make a layer class. A layer class is going to have a set of inputs. It's going to have a set of outputs because the layer needs to know, if I have, for example, 5 inputs coming in, am I going to have 3 inputs in the next layer? I'm going to have 4 inputs. So this is pretty straightforward. I do self.neurons is, I'm going to say for each of these neurons for each I in range and out. So basically, each neuron is going to take in all the inputs. And how many neurons are we going to make? Well, the number of outputs that we want. And again, the call function is dead stupid here. We're going to say that the list of outputs is going to be for each of the n neurons, I just want to call n of x. There we go, right? Go ahead and return that. I'm gonna just return outs. Let's keep it simple. So return outs for now. Let's actually do this. If len of outs is 1, so for example, if it's like a singleton list like that, let's just return the actual value. Otherwise, we'll return outs. That's just a little cleaning up right there. But now if I do x is equal to 2 dot 3 dot, so if x is 2 and 3, that's my input. And let's say I have a neural net that takes in this case, 2 inputs, and it returns 3 outputs, right? So I've got 3 neurons that are stacked on top of each other, right? So you can think of circle, 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 3 of these circles. Each of these neurons are taking in the 2 inputs, which in this case in 2 and 3, and they're firing. And now let's call n of x. Boom. We have a 1-layer neural network. Look at that. Now you guys are thinking, okay, Saad, that looks like pretty stupid. Like that doesn't seem kind of cool. Well, what if I did this for you? What if I did draw dot of n of x? It doesn't work. Give me actually just 1 second, guys. 1 second. Oh, yeah, because n of x is the entire layer. Sorry, guys, we can't return yet. We're almost there. We're almost there. This is 1 layer. We need to have multiple layers, right? MLP is the class that we're going to call it on. So what is MLP? It's a multi-layer perceptron. So finally, I'm going to have my inputs. X in this case is, it is a vector of 2 elements. I've got 2 inputs. How many outputs do I want? I'm likely going to have 1 output. So the size is going to be pretty simple. It's going to be a list of basically however many inputs that I want plus outputs. So I'm going to basically have these layers, right? So these layers are going to be for I in range, len, n out. So how many output neurons do I want? For each of those, I'm going to basically have a layer. And that layer is going to say, okay, each of the layers, I'm going to have, the SZ in this case is a list that represents, the size of each of those layers. So I'm going to have a layer. It's going to be SZ of I up until SZ of I plus 1, right? So these are my layers. And again, calling it should be super basic. So self X, or each layer in self.layers, X is equal to layer of X, right? So we're just applying each of those layers, right? Okay, I'm just gonna run this one more time. Let's see if this will work. Draw dot. Just one second, what's going on here? Just a minute, there's definitely some bug here somewhere that I'm gonna show you guys in just a second. Just one second. The problem is all my cells are running in different orders. It's funny. Let me just run my value cell one more time. That's the one that actually matters. And then one more time, let me run my neuron cell, my layer cell, run that over there, and then see what that should work. There we go. Sorry about that, guys. This is one neuron right here, right? So I ran n of x on this layer right here. And what's kind of cool is that when you have an MLP, you have an MLP that's going to be much more complicated. And it's this giant thing right here. So now you see we're building these giant neural nets. See how giant these are? So this is what's going on here is that, again, I'm going to, let me run this layer cell one more time. So if I just have one layer, right? And if I call draw dot on n of x, might have been on like this. Sorry, guys, I think it's something to do with just the order in which I'm running all my cells again. So let me just run that one more time. But basically the idea here is that we've built a multi-layer perceptron where we have one neuron, and that neuron takes our values, it multiplies them by these, it takes the input, it multiplies them by their weights, it adds a bias. We stack these neurons into one layer. We stack these layers into a multi-layer perceptron, and now you get this like super ugly looking thing, which is, all the way at the output over there. And guess what we're gonna do on this output? We're gonna run the backwards pass, right? So now I can take this n of x, right? And I can run backwards, right? And I'm gonna do that basically in just a second. Sorry, just one sec, guys. I'm gonna restart my terminal. And when I run backwards on all of this, it's gonna go ahead and fill. I don't know if this will work. Oh, did it? Yeah, the reason it's not working is I need to tweak the code a little bit such that it doesn't use random numbers. But the idea here is, once we run our backwards gradient, we're going to be able to fill in every single one of these gradients. I'm over time, so I'm going to end basically with just 2 more minutes, and I'm going to kind of show you the completed lesson plan. But the idea here is, again, you got this like giant mess of, a neural network, which is basically all of our inputs, and you're seeing how they feed into each of the weights and all the layers. It's okay if you can't make sense of this. But the idea here is that at some point, you're going to be able to have multiple data points. This is a data point, this is a data point, this is a data point. And you're going to have a prediction, right? So let's say, for example, this is a very basic model. We want this data to predict these output values, right? So you can see right now, we don't do that. Right now, our weights are initialized as random, right? So you can see that each of the values is just a totally random value. And we're trying to get to this data, but obviously our weights are so random. So the thing that we're going to talk about next time in next class, guys, if you feel lost at this point, it's just because we're kind of bleeding over into what I wanted to talk about next time, which is how do I have a loss, right? And how do I take my multi-layer perceptron right here, and how do I basically adjust my loss by adding the gradient over and over and over again until my loss goes down to zero. And that's what you're seeing right here. Do you see how I called n dot backwards on the loss function right here? And I have this giant mess where the gradients are filled in. So the topic for next class is going to be, okay, that last piece that I just blitzed through, what the heck is gradient descent? And okay, Saad, I understand how to calculate the gradients, but how do I use these gradients and fiddle each one of these knobs such that my final loss function is as low as possible? All right. Okay, we're basically at time. Forgive me. The last part we kind of sped through. But again, the focus of this class's lecture was just, and yes, Joshua, I'll send this code over. But the focus of this lecture was as simple as how do we make an engine that is capable of doing additions and multiplications and then calculating a backpropagation. So this was the interview question that I used to ask at Essential AI. Excellent, guys. If anybody has any questions, we can answer those in the chat for the next couple of minutes. In the meanwhile, I'll debug what happened to just that lecture. Yeah, any questions so far? We have exercises for us to work. No, Bilal, there'll be no exercises, but I will give you guys the Python notebook that I worked through. Yeah. Yeah. Any questions, guys? Everything is straightforward.
So Saad, you worked at Essential AI. Can you explain like the background of that company for those who don't know?
Yeah, sure. I would love to even share my screen. But Essential AI, basically, their focus. So Ashish Vaswani is the primary author on the famous "Attention is all you need" paper. So what we're going to talk about in our third lecture is we're going to re-implement this paper. This paper is the one that basically invented the first GPT. Right, so the first transformer model. And each of these people, they're very, very well respected machine learning engineers. Nikki Palmer, for example, is Anthropic. Noam Shazier, is at Google now on DeepMind. Aidan Gomez is doing Cohere. So Ashish went and made his own lab called Essential AI. Their entire focus is we were working on training our own open source model. And this is going to come up over and over again when you guys become machine learning infrastructure engineers. But open source models are amazing, right? Like there's so much flexibility that you have in being able to run a model on your own infrastructure as opposed to, reaching out to something via API call. So we were trying to make, because unfortunately right now, all the open source models, the best ones are all Chinese models. There are no good American open source models. So we were trying to make some. Yeah.
Amazing. Saad, can you go back to your code for a second? I want
Sure.
everyone here, you all stuck to the end. I think that shows a lot of dedication and effort. Please take a screenshot literally of, what do you see here with the
This giant neural
visualization,
net
the
right
graph.
here, right?
Post it on LinkedIn, tag Saad, thank him for his time. And also, I'm going to drop a link here to the next workshop that Saad is doing next week. So please take a screenshot here, post it on LinkedIn, show that you're being active, in learning. And, I just sent a link for the next week's workshop. So please, post on LinkedIn, add the Luma link in your post as well. Encourage more people to come as well. Invite your friends. Um, obviously, oh, Saad, can you share so you met Ashish Vaswani at an event, and apparently he gave you a job offer on the spot. So
Yeah, no, I mean,
what
that's
did
just the
you
benefit
tell
of
him
networking.
to?
I had told
Yeah.
him that I was looking for a job, that I was dropping out of law school. I was coming back to San Francisco and I don't really know what to do with my life. And I told him about my experience, about my background. He had a research lab, essentially, I obviously that he was getting up and running off the ground. And I had told him my experience at Tesla, and he was like, "Oh, well, we need someone just like you. Please come to the office tomorrow, and we'll give you an interview." And gave me an interview, passed the interview, and got the job. So
Wow.
yeah.
So this was this after you left Tesla or were you still at Tesla?
Yes, this was after I left Tesla. This I had actually
Okay.
even gone to graduate school and decided to drop out.
Hmm.
Yeah,
And
some
how
people
did
asking
you
questions
I
about
see.
what made me drop out of law school. Those are
Yeah.
stories for another time. Right. Yeah, there are a couple of questions in the chat for them that I can answer really quickly.
Sure, sure.
So, thank you for your time. Any books, articles, or tutorials I'd recommend you guys to read? Yes, D2L.ai. This is the best primer on machine learning. It's really slow and in depth, and it starts you from the basics. And the great thing about it is if I scroll down to the structure of the textbook, it kind of shows you, sorry guys, in the preface, it should be here somewhere. Yeah, this textbook, its chapters are structured like this, where you can, like we did, for example, chapter 3 and 4 today, and then a bit of chapter 5. Right. And you can go in any direction. And, we're going to try and target chapter 11, which is on attention mechanisms. That's the number one resource, which is D2L.ai. I'm going to drop that in the chat. Love this textbook. It's a bit slow, though. I also like Andre Karpathy's Zero to Hero series, right? We went through episode 1 and 2 of this. So, right there, that's what we did. We built micrograd. Cool. Let's see, any other questions? Somebody asked, what is a real world use case of what we built today? So the MNIST database, I didn't go through this, but I could have loaded up this database. And the neural net that we trained, this is the exact multi-layer perceptron was, engineered in the 1970s, and it was used to solve this data set. So yeah, you could probably get like 90% accuracy on this data set. So you can predict numbers from images. You can do a bunch of things, but yeah. Um, let's see, anybody else? Someone's asking at the end of this course, can we train GPT models for our own specialized use cases? Yes, but I wouldn't recommend it. If you, what I would recommend instead is taking an open source model and fine tuning it, which we'll talk about that later. See anything else? Are students able to solve this in an interview? Yes. If you give someone the value class, it's less than 150 lines of code, what we did today, right? So implementing backpropagation is quite straightforward. Actually, one thing that's pretty cool that I didn't get the chance to show you guys, I'll show whoever's still stuck around. If I go to some real PyTorch code, like this is the PyTorch repo, this is a C++ file. Like I said, PyTorch is a Python package, but the underlying code is written in C++ to take advantage of parallelism features either on your CPU or on your GPU. So you'll see here, for example, there's a CPU, there's a CUDA, there's all the different devices that this thing could be running on. So if I were to run the tanh function on PyTorch, this C++ code gets run, which is really ugly. It doesn't matter. No human being ever reads this thing. But if you see right here, the backwards function for tanh, remember what we had calculated? It's 1 minus tanh squared. Look at that, right? So, you see that in the PyTorch code as well. Let's see. Yeah, I guess nobody else is asking technical questions. Everybody else is asking about how to learn more about machine learning. So just stick around for these workshops and,
Can they get a link to the code or no?
yes, 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 of course, of course. We'll send that afterwards.
Yeah, and please, for the folks asking, we'll send a recording, we'll send the link to the code and whatnot. Um, so just stay tuned for email after.
Awesome. Cool. All right, Faizan, I'm gonna hop off.
All right.
Yeah, thank you so much, guys. Yeah, it was fun to walk through this with you guys.
All right.
Thank
Yeah,
you.
thank you everyone for joining. And please, while Saad is here, please take a screenshot. Literally just take a screenshot of this code and the MLP code. Or yeah,
Yeah, I
maybe
like this
show
language
the
a lot.
equation, make everyone look smart and post on LinkedIn. Like I said, posting on LinkedIn has changed Saad, would you say it has changed your life?
100%, of course. Yeah. I think definitely for the business, ever since we got into the startup world, I used to not really care about social media a lot. I used to really hate it. But ever since we got into the business world, we realized that, okay, it's just an amazing vehicle for reaching out to customers, for hiring people, right? I have to hire engineers.
Mm,
So, those LinkedIn posts and really understanding what a person's experience is comes very much in handy. So I
mm,
completely revamped my entire LinkedIn as soon as we started the business. So,
mm.
yeah,
Nice, nice. Yeah, so please, take a screenshot, post on LinkedIn. The more active you are on LinkedIn, I strongly believe the more opportunities come your way. I myself am trying to post more. And I guess while we're on the topic and I see someone asked, I'll just share my LinkedIn in the chat. So, like you see, my co-founder, he's way more active on LinkedIn than me. He actually hit over 50,000 followers on LinkedIn. And so, when you have a reach of that many people, it kind of opens up a whole world of opportunities. Like we're posting 12 hours before a meetup and we get 100 people to come. That's something that's very hard to pull off. And so, if you gain a bigger following on LinkedIn, you might have recruiters reaching out to you. Um, and so it just opens up world of possibilities. So, and I will say,
awesome.
obviously, Saad, as his company grows, he's looking to hire engineers. I'm sure he would be interested in anyone who's stuck through his lectures and, is eager to learn. So maybe he's gonna look into our network for hiring. And obviously, we as Headstart, we're always, keeping our eye open for talent. And for anyone who we see, who attends these workshops, is active on LinkedIn, they're definitely on our radar. So just wanted to mention that. Yeah, I shared my LinkedIn in the chat. And also just want to share briefly, I think maybe we'll share more in the next kind of workshop, but we're just kind of relaunching Headstarter as a new kind of platform. So I just shared the link in the chat. Um, so at Headstarter, we're building a platform where engineers can compete with each other along with AI to build projects to build things like this. And so we're in the pretty early stages of like our building our platform. We're just gonna revamp the whole thing the past couple of days. But yeah, maybe just take a look at it, get your rank, your career capital score, and please share any feedback with me as well. We're actively looking to improve the platform. And yeah, any feedback would be really appreciated. Anything I can build on our platform to help you all, that's like my top priority. And so, well, for you all to check it out, try out the platform, and just let me know what do you think. And Saad, you too.
Yeah, definitely, of course.
You're trying to debug your code right now?
Yeah, I'm just taking a look. So basically, you can see right here, if and this is the code that I had written up myself before I started, but I've got a neuron, I've got a layer. If I have one layer that has, let's say, two inputs and three outputs, and if I have a multi-layer perceptron, right? So I can call draw dot, and you'll see all the gradients are 0. And then if I run backwards, now the gradients get filled in, right? So backwards propagation ran. I'm just trying to debug while I was doing this live in front of everyone. What mistake did I made that my gradients are still showing up as 0?
Wow,
Um,
cool. So Saad, are you coming to the event? Or
yes, or yeah,
oh,
we'll
you
see.
are.
We'll see. Yeah, yeah, yeah.
Okay.
Okay. Oh, we'll hop off then. Yeah, I think we should end the call.
Yeah. So
Yeah.
for those of you in SF, this is something that's, unique to SF. We're actually hosting an event that's going on right now with founders of many, dev tool companies, from Whisperflow, PostHog, Incident.io, and a bunch of other companies. So that's actually going on right now. Saad and I are literally about to go Uber to the event right now. So pretty busy day. Only possible in SF. So if you aren't in SF, do everything you can to try to be here. It changed my life. It changed, well, Saad, you were born here. But I guess that's
Yeah, but I
yeah,
never lived in the city. I was always living in South Bay, and that
oh
was really boring and didn't like that.
yeah, but
Yeah.
South Bay doesn't count. You have to be in SF within
Gotta be
like
in
a
SF.
it's like a 2 by 4 mile radius or whatever. Um, so the area I'm in is North Beach, and if you're in North Beach down to like Mission, um, this is where the smartest people in the world in AI all are. So this is the place to be, if you want to build something great or just level up your career. All right, so we're about to hop off now to go to the event, but please connect with Saad and I on LinkedIn. Share any feedback with Saad as well. I'm sure Saad, maybe
Yes.
next
The
time.
feedback is probably talk slowly, but anything other than that,
Yeah,
I'd be happy to hear.
yeah.
Yeah.
So, please share any feedback, and yeah, we'll see you all next week. Well, with Saad again. All right.
All right.
So
Cool,
take care,
guys.
everyone. I'm gonna
Thank you.
end it now.